Hi friends, in this video we can start transmission lines. So before starting a transmission lines we will know what is a transmission line. A transmission line is composed of two conductors wherein we apply some voltage at one end called source, and we see that the entire power and the energy which we have applied on one side, it is reached to the other side. Okay, so if I consider this as a transmission line and these are my ends of the transmitter line, here I have a load, so I call it as a load impedance. It's a load impedance, and this is my source or generator. Right? So whenever I am applying a voltage or energy on source side and it is reaching the, and it should reach entirely to the load side. That means efficient utilization of power should be done from source to load. Okay, so suppose these are my ends AA dash and these are my BB dash. I'll come to you what are the applications of transmission lines and like we will use this transmission lines in the video lecture later. But for the first thing is we need to know like what is a transmission line and the equations governing the transmission lines. So in this here AA dash are my ends and BB dash are my ends. These are the energy which is flowing from source to the load will be in the form of waves. So whatever the energy I am applying here will travel through these transmission lines to conductors and reach this load in the form of waves. But this transmission line, these conductors, both the conductors are not we'll be having some resistance and reactance covered with some other elements, passive elements. Okay, so these are not ideal conductors. There may be some losses. So whenever we give some energy, there might be some reflections coming back to the generator. We'll get into that, like how the reflections are taking place in this medium. But first we need to know what does this transmission line consists of and what are the equations governing that. So let's say this is my transmission line and of length L. Okay, now here at AA dash point I am applying the voltage, sinusoidal voltage here. Let's say I have applied at AA dash, my voltage peak is at this point. After reaching this distance, after traveling this distance at BB dash, my voltage peak can be here or else here, anyway. So what I am saying is whatever the voltage which we are applying here, that after traveling some distance for some time, okay, that might change from some peak level to the other peak level. It constantly varies with the time. So that time that time which this wave is traveling in the transmission line is called transit time, which is given by the entire length by velocity of that wave. So the wave from this point to this point is traveling with the velocity v and it is covering a distance of length L. Okay, this transit, whenever we consider the transmission line, we will be having this transmission line effect. Okay, the first thing is that the effect which is due to the transmit time is called transmit time effect. So we can ignore this transit time in only one condition, whenever there is the time period of that wave which is greater than this transit time. That means if this is the this is the time period of this sinusoidal wave, and if this time period is far greater than this transit time, then is the case we are ignoring the transit time effect. That means this transit time, this is 1 by f of the frequency, and this is far greater than L by V. Okay, and if you cross multiply this, we know that velocity upon frequency is given by lambda, that is wavelength. Okay, whenever lambda wavelength, this transmission line is far greater than the length of the transmission line, then we can ignore the transit time effect. Okay. Now, to analyze this transmission line, what we do is we take few parts of the transmission line, because we cannot entirely govern this or analyze this transmission line, because it is of huge length, maybe some 10 to 1000 kilometers. So we will take some part of the transmission line and see what is going on in that part, so that we can govern the entire transmission line. Now if I take some part of this transmission line and see, let's say this, some part of the transmission line. So it has a magnetic field induced in the form of inductors. It has two resistive elements. Okay, it has two resistive elements. One is resistor, that means the resistor along with there is a conductance. And there is another passive element called capacitor C. Okay, so if I cut this transmission line into parts, and if I view that one part, then it is having that resistance, inductance, capacitance and conductance. Okay, here these four parameters or these four elements are called passive elements, and they are said to be the primary constants. Okay, and here these all are defined for unit length. That means this is ohm per meter, this is Henry per meter, this is farad per meter, this is mho per meter or psi per meter. Okay, this is the way they are defined in transmission lines. Those are all defined for unit length, because we are taking some part of the transmission line, a unit length part of the transmission line, say 1 meter, and we are defining them. So they are given by per unit length or defined per unit length. Now next is the case that we got the elements here what are present in some part of the transmission line. Okay, now the next thing we need to do is to jump on to generate or to derive the equations which are governing this transmission line. So I'll take a transmission line part, and it looks like this. It has an inductor, a resistor in series, a capacitor and a conductance element. Okay, so this is of delta x length. I'm considering this to be some delta x length, so this should be L delta x, right? And this should be R delta x, C delta x and G delta x. Okay, now if you can see that here I am applying a voltage of V. Here I am applying a voltage of V. Then at the output I am expecting a voltage of delta V plus delta V. Similarly, I am applying a current I. Whenever I apply voltage V, I get a current I, and I am taking the output current as I delta V. Because some of the part of the, it's not like, because we have the resistive and reactive elements, it's not complete energy which we are giving will get at the output part. There will be some dissipation of the energy due to capacitor and inductor. They save the energy or store the energy, whereas reactors and conductors, they dissipate the energy. So there might be some changes in the voltage and currents which we get at the output. Okay, that's why I'm taking the delta I and delta V changes. Now we have applied the voltage V and we have got the current and we got the voltage relations. Now we'll start, we'll see what is the change in the voltage. Delta V, like V we get, so what is the change in the voltage delta V? That is R, that is R plus, this we take as j omega L frequency, where omega equal to 2 pi f. Okay, the frequency of the wave into delta x. Delta V equal to R plus j omega into delta x into I, into the current I, negative side here. This negative side indicates that energy is dissipated. Okay, and similarly the relation for the current delta I is given by minus G plus j omega c into delta x into d. Mark the first equation and this is second equation. Okay, now if you take delta x on the other side, delta V by delta x is given by minus R plus j omega L into I. This is delta V by delta x equal to minus G plus j omega c into V. Okay, now apply the limit. Apply the limit, delta x tends to 0, because we want to consider the entire cable and we have started with a small part and I am approximating it to 0. Delta V by delta x equal to minus R plus j omega L into V. Limit x tends to 0. Delta I by delta x is given by G plus j omega c into I. Okay. Now here, limit and differential delta operation. So this is small change and we applied limit. This is differentiation. You can take it as differential operator. dV by dx is R plus j omega L into V. Similarly, di by dx is minus G plus j omega c into I. Okay. Now wait. This is into V, right? Into V. Okay. Now here I am applying the differentiation for the first equation. D square by dx square is equal to minus R plus j omega L into di by dx. Okay, so put the second equation in the first. We have R plus j omega L into G plus j omega c into V. Is that correct? And just replacing this equation in this, so I got this equation. Now this entire term is given some name called gamma. Entire term is called gamma, which is called the propagation constant and one of the important parameters of the transmission line. Okay, this gamma helps us to know whether that line is the transmission line is lossless or low loss. We'll come back to what is lossless and low loss after few lectures. But here this gamma plays an important role in the transmission line theory. So this gamma is given by R plus j omega L into plus j omega C. Okay, let's take gamma square, and you can see that this is both these are the complex terms, and this is a complex term expressed as alpha plus j beta. Okay, now this gamma is alpha plus j beta is given by under root r plus j omega L into g plus j omega C. Right? Now we have this equation, right? So I'll define what is alpha and what is beta in the later videos, okay, in the next video if possible. And for now it is taken that d square by dx square is gamma square of v, right? This is one equation. Let it be equation number 3. Similarly, we get another equation for current, dA square I by dx square equal to gamma square into I, right? If we get the equation for voltage, similarly we get the equation for the current. Okay, I'm not doing that again. And so now these are the differential equations of second order. We know that we have some formula for solving the differential equations like particular integral and complementary function. So using that, as it is a homogeneous equation, directly we have the formula for this kind of equations. Okay, whatever the variable will express in v of x, so I will take it as v of x equal to v plus e power minus gamma x plus v minus e power gamma x. These two are the terms. They play another important role like propagation constant in the transmission line. So whatever the terms I am taking here, v plus and v minus, they have certain meaning. They have certain meaning, and they are defined so because I'll tell you after completion of this the next sentence. Now, as I said earlier, whatever the transmission line, whatever the waves they are, and they are traveling from the generator to the load, they are all time variant. So I need to consider even the time element here. What I will do is v plus into e power minus gamma x plus v minus e power gamma x into, and multiply it with the time element e power j omega t. Okay. Now this becomes v plus into e power minus gamma x into e power j omega t plus v minus e power gamma x into e power j omega t. Okay, and no need to again write like, okay, I'll write it. Similar is the case with the current. I plus e power minus gamma x e power j omega t plus I minus e power gamma x e power j omega t. Okay. Here in this case, we have got this term with respect to time and with respect to the length we have considered x. Okay. Now I'll explain what are these terms by taking this term, only one term, and I'll tell you. So, and the equations I told, which are the governing equations of transmission lines, are these two, 5 and 6. This should be remembered, and we will use these equations in many areas for calculation of impedance, for calculation of VSWR, for calculation of load impedance, etc., etc. So you need to remember these equations, right? Now I'll explain what is this term specifically. So here v plus e power minus gamma x into e power j omega t is given, right? Now here I said gamma is alpha plus j beta. V plus e power minus alpha minus j beta into e power j omega t. This is v plus into e power minus alpha x into e power j omega t minus beta x, right? Okay. Now here, and where here alpha is attenuation constant. Alpha is attenuation constant, and beta is, I'll tell you what is beta. Okay. Alpha is attenuation constant. Why it is called attenuation constant? Constant is e power minus ax into v plus, right? Like if you consider this graph, when x equal to 0, my amplitude is v plus, and it starts from here, and it's a decaying function, e power minus gamma alpha, so it starts on decay. That means the amplitude whichever I have given at the generator side is not entirely reaching the load impedance side. That means it's slowly decaying and it is tending to 0 at some point. Okay, it won't be 0 actually, but it's tending to 0 at some point. So this is called attenuation constant. That means it is attenuating the amplitude of the wave at certain point, and it is making it to very low amplitude or tending to 0. Okay. Now I'm taking like there is no attenuation. I'm considering there is no attenuation. Then this will be v plus into e power j omega t minus beta x. As it is real time situation, I'll consider the real part of e power j omega t minus beta x. We know the real part of e power j omega t is cos. So cos omega t minus beta x. Right? Now it is a time dependent. Omega t minus beta x. So what I'll say is, suppose this is a time t equal to t1, t equal to t2, t equal to t3, and this was my first wave, second, third. Now suppose at time t equal to 0, my peak is at this point. Next, then my peak will be at here. Next, my peak will be at here. That means there is a change, or there is a slight variation in the peaks of at different time intervals. That is due to this cos omega t minus beta x. This is making the wave particle from position change from one position to other position at different times. Okay. Now this is omega t minus beta x for the first case I have taken. Similarly for the next case it will be omega t plus beta x. Whatever the generator I have considered here, I have taken it for like this, and I consider this as positive x direction. Okay, so here this is positive x direction for us. So for x equal to 0 to some distance x is changing in the rightward direction. Suppose if you consider the next part of the equation, v minus into e power, that will be, for the next case is e power gamma x into e power j omega t. This will be e power alpha x into e power j beta plus omega t, j beta x plus omega t into j. Okay, this will be in positive direction. That means the variations will be like this in the opposite direction. Okay, so this is importance of this term in the equation. It shows the variation from the wave in which direction, from which direction to which direction. Right? Now then is, I told I'll define the beta, which is called the phase change, right? So we know that alpha equal to alpha plus j beta, and as I said, beta x is the thing which is changing the phase. So I'll take that phase change is minus beta x. which I have got in the earlier equation. So beta is defined as phase change per unit length. Phase change per unit length. So from the basic physics we know that for wavelength of distance there will be change of 2 pi phase. Now for beta, how much is the phase change? Right? For beta of length, or for x, it will be 2 pi by lambda. Okay? Or else this should be in the reverse manner. Okay? Beta should be 2 pi by lambda. Okay? For beta phase, how much is the change? It is 2 pi by lambda. Right? This is called a phase constant. Beta is called phase constant. Alpha is called attenuation constant. Okay, and if suppose there is any value we need to calculate at any instant of time, we can calculate that using this equation. V of t equal to, considering the real part of v plus e power gamma x into e power j omega t plus beta x. Using this equation we can find out whatever value at time t, we get the voltage value. Okay, so by here with this I'll stop this video here and I'll stop this lecture here. So in this video what we have learned is that how a transmission line looks and what are the equations governing the transmission lines, and what is the attenuation constant, what is the phase constant, and how does the phase change occurs from source to generator. Okay, now in the next video we'll be dealing with what is the characteristic impedance and how do we calculate the impedance at different points on the transmission line. That's all for this video. Thank you.